In this presentation, I'll be going through mole concept calculations. I think the main things I'll be covering will include number of moles, stoichiometric calculation, and percentage yield. This is a summary showing how we can obtain the amount of substance. We can obtain the amount of substance from the number of particles, the mass of substance, and the volume of the gas. To obtain amount of substance from number of particles, we will just simply find out what is the number of particles divided by the Avogadro's constant. To find out amount of substance from mass of substance, we will use the mass of substance and divide it by the molar mass. To find out the amount of substance from volume of gas, we will simply find out the volume of gas at standard temperature pressure divided by the molar volume at standard temperature pressure, which will be 22.4 dm³. As gases can expand, so there's such a thing called molar volume at room temperature pressure, and that will be 24 dm³. Do take note the difference in temperature for standard temperature pressure and room temperature pressure. For standard temperature pressure, it is 0 degrees Celsius or 273 Kelvin, while room temperature pressure it is 25 degrees Celsius or 298 kelvins. The calculations based on mole ratio will require the following for you to take note. Stoichiometry is the quantitative relationship between quantities of reactants and products involved in a chemical reaction. It is based on balanced chemical equation and the reaction between mass and mole. The substance will react in a simple ratio of their moles. An example that I would like to give you is firstly, how many moles of carbon dioxide and water will be produced by the combustion of 15.0 moles of CH4, which is also known as methane. First and foremost, always write a balanced chemical equation for the reaction, which is just methane, 1 mole of methane plus 2 moles of oxygen to give you 1 mole of carbon dioxide and 2 moles of water. Essentially, the mole ratio is for every 1 mole of methane, you will produce 1 mole of carbon dioxide and 2 moles of water. Therefore, the amount of carbon dioxide formed will be 15.0 moles, and the amount of water produced will be 2 times 15.0, which will give you 30 moles. Since 2 moles of water is formed together with 1 mole of carbon dioxide, therefore, the amount of water formed is twice of that of the carbon dioxide that is formed. My second example, calculate the volume of hydrogen gas evolved at standard temperature pressure when 36 grams of magnesium reacts with excess hydrochloric acid. Once again, always write a balanced equation of the reaction, which is 1 mole of magnesium reacting with 2 moles of hydrochloric acid to give you 1 mole of magnesium chloride and 1 mole of hydrogen gas. The amount of magnesium reacted will be just 36 divided by 24.3 to give you 1.482 moles. Why do we make this calculation? Is because 24.3 is the AR of magnesium. The amount of hydrogen evolved will be 1.482 moles. The volume of hydrogen evolved will be 1.482 multiplied by 22.4. That's because the molar volume at standard temperature pressure is 22.4. That will give me 33.18 and will change it to 33.2 dm³. Now do take note that the final step is in 3SF and the intermediate steps are in 4SF. We left the intermediate steps at 4SF for neatness and to preserve a certain accuracy in the final answer. It is not necessary to have more than 4SF in the intermediate steps. My third example, isooctane C8H18 undergoes combustion efficiently in automobile engines. It is given an octane number of 100. What mass of oxygen is used in the complete combustion of 2.0 grams of isooctane, and what is the volume of carbon dioxide produced at standard temperature pressure? Once again, it's important to write the balanced chemical equation, which gives you a mole ratio that for every 1 mole of isooctane, C8H18, you will require 25/2 moles of oxygen that will produce 8 moles of carbon dioxide. Hence, for the molar mass of C8H18, we can obtain it by having 8 times 12 plus 18 times 1 to give me 114.0 grams per mole. As a result, once you have the mass of isooctane as well as the molar mass of isooctane, you can find out the amount of isooctane. Simply is the mass divided by the molar mass. We are able to obtain the amount of oxygen found, or should I say, we are able to obtain the amount of oxygen used, which will simply be 0.01754 multiplied by 25/2. That's because for every 1 mole of isooctane, you need 25/2 moles of oxygen. The mass of oxygen used will therefore be the number of moles of oxygen multiplied by its molar mass, which is 2 times 16. That will give me 7.02 as a 3SF answer. Do once again take note that the final steps is in 3SF and the intermediate steps are usually in 4SF. We can also find out what is the amount of carbon dioxide being produced because we are able to find out the amount of isooctane used. So 8 multiplied by 0.01754 will give me 0.1403. Hence, we are able to calculate the volume of carbon dioxide produced at standard temperature pressure, which will be the number of moles of carbon dioxide produced multiplied by the molar volume at standard temperature condition, which is 22.4. That will give me 3.142, or rounded off to 3.14 dm cubed in 3 significant figures. Now we would like to go through certain definitions that are required in stoichiometric calculations. Firstly, I would like to define what are limiting reagents. Now, when we talk about exact amount of substance required or produced by a chemical reaction, that is what we call the stoichiometric amount. When all the reactants is entirely used up, when the reaction goes to completion, we will consider this to be limiting reagent. However, when the reactant is still available despite the reaction going to completion or have been completed, this refers to an excess reagent. Now, limiting reagent, what you need to take note about limiting reagents include when there are an excess or more than one substance available for the chemical reaction. The reaction will stop when one of the reactant is totally used up. The starting amount of the limiting reagent determines the maximum amount of the product that's formed. So that's why it is important for us to know what are the limiting, or which is the limiting reagent. By knowing which is the limiting reagent, we will be able to obtain a guess or a sense to what is the maximum amount of the product that is formed. First, I would like to share with you an example of how limiting reagents can be determined. For a reaction that shows 2 moles of magnesium reacting with 1 mole of oxygen to give me 1 mole of magnesium oxide, given that you have been given 1 mole of magnesium and 1 mole of oxygen for this reaction, you would realize that you will only need half a mole of oxygen to react with 1 mole of magnesium. Hence, you can tell quite easily that the magnesium is the limiting reagent, whereas oxygen is the excess reagent. A second example of limiting reagents, this time round I'm using the reaction between sodium and chlorine. We obtain the mole ratio of 1 mole of sodium to half a mole of chlorine. You are also given the amount of sodium and the amount of chlorine, and we can find out which is the limiting. the amount of chlorine required will be 0.25 moles, which is far less than 0.563 moles that you have available. Therefore, you can tell easily that sodium is the limiting reagent. Now, for another example of the limiting reagents, we can continue by asking ourselves, so what is the mass of the product that is formed? Now, once you know which is the limiting reagent, you would know that the limiting reagent is sodium. The mass of sodium chloride formed will be 0.500 multiplied by 23.0 plus 35.5 to give you 20.3 grams. Do note that you know that 0.5 moles of sodium was given at the start, and sodium is the limiting reagent. You are therefore able to calculate the mass of the reactant present that remain unreacted. So the excess amount of chlorine will be 0.563 moles of chlorine that you have, minus of 0.250, which is the amount of chlorine reacted. That will give you 0.313 moles. Hence, the mass of unreacted chlorine will be equals to 0.313 multiplied by 2 times 35.5, which will give you the molar mass of chlorine. So I will obtain 22.2 grams of unreacted chlorine. Some notes that you should take note when you are doing calculation in stoichiometric calculations. First thing, write the balanced chemical equations for the reaction. Convert mass of reactants used to moles and determine the limiting reactant. This is sometimes applicable, but you need to double check in case it is. Calculate the required quantity of reactant or products used using the mole ratio method, assuming that the reaction goes to completion. Now, these notes provide you with an aid to how to perform stoichiometric calculations. Now, another concept in stoichiometric calculation is to talk about theoretical yield and actual yield. Theoretical yield tells you the amount of products formed theoretically, while actual yield is the actual amount of product. These numbers may not be same due to various reasons, such as the reaction not going to completion because of by 100% conversion. That is probably because when you form the products from the chemical reaction, you will need to purify the product, and some amount of the product could be lost. And when you have lost a certain amount of product, your actual yield is actually much lesser than what you have anticipated from the theoretical yield. Hence, to calculate the theoretical yield and compare it to the actual yield, we will do the following. First, write the balanced chemical equation for the reaction. Secondly, convert mass of reactants used to moles and determine the limiting reactant. Calculate the required quantity of the reactant or product using the mole ratio method, assuming reaction goes to completion. Now, to calculate percentage yield, what happens here you need to do is percentage yield can be obtained by, firstly, the actual yield divided by theoretical yield multiplied by 100%, or you could actually see is the actual mass of the product formed divided by the calculated mass of the product multiplied by 100. The next example, in the reaction between sulfur dioxide and oxygen to form sulfur trioxide at a temperature of 450 degrees Celsius and the atmospheric pressure, 6.4 grams of sulfur dioxide in the presence of excess oxygen produce 7.6 grams of sulfur trioxide. Calculate the percentage yield of sulfur trioxide. Note that this reaction is a reversible reaction, but we will still in this case assume that it goes to completion. From the reaction equation, we can see that for 1 mole of sulfur dioxide, 1 mole of sulfur trioxide is being produced. Therefore, the molar mass of sulfur dioxide can easily be calculated using 32.1 plus 2 times 16 to give me 64.1 grams per mole. Hence, the amount of sulfur dioxide used will be 6.4 divided by 64.1 to give me 0.09984 moles. whereas the theoretical amount of sulfur trioxide produced would be 0.09984 moles. That's because the mole ratio of sulfur dioxide and sulfur trioxide is 1:1. Alright, so the molar mass of sulfur trioxide is 32.1 plus 3 times 16, that will give me 80.1. Hence, the theoretical mass of sulfur trioxide that can be produced would be 0.09984 multiplied by 80.1 to give me 77.997 grams. Now do take note that 0.09984 is the theoretical moles of sulfur trioxide form because the sulfur dioxide and sulfur trioxide is in the 1:1 mole ratio. Hence, the percentage yield of our sulfur trioxide will be 7.6 as given by the question, divided by your theoretical mass, that is 7.997, multiplied by 100, that will give me 95.0%. Thank you for watching this video. Please repeat this video if you think it is necessary.